just a class opening ceremony, and then we can start the lecture. So welcome all to the Brazilian ICPC Summer School. This year we have like as sponsors Huawei as a premium sponsor, PTG Pactual and Unicamp as a gold sponsors, and as silver sponsors Canals and Neon, and as bronze sponsor Google. So this is a chart showing the participation over the years. Let's go back to 2012. So we start with a smaller school, and we grew bigger around 2019. And this is the largest school we had until this date. We did some arrangements in the auditorium so we can have a little bit more of students here. I know it's very crowded, but the idea was to receive as many of you as we could. Okay? So we always had ICPC finalists in our school, and now we have the Latin American finalists. So we have 80 Latin American finalists. Most of this class are Latin American finalists. Show hands which is Latin American. Okay? And we have a lot of other participants in this class and in the other class also. So we even topped the number of students that we had online when we didn't have the room capacity constraint. Okay? From our students are all over the place. So you have Argentinians, okay, Brazilians, Chile, Colombia, Mexico, Peru. Yes, no? Oh, they had some problem with the flights. And Uruguay. And we have people from Brazil from all over the place. And so this is a map from with a dot for every location we have a student. So we are very proud to receive people from all over Latin America here at the school. Also regarding female participation, in 2019, we had only 8 female students at the school, and note that the school was not small. It's not like we had a lot of students. Then in 2020, we start giving a fee waiver, so female students start to be exempt from registration fee. And we start giving financial support for some students to come to the school, paying their flights and their stay. So this number grew a little bit. And this class, this year we have the largest participation of female students we ever had. Okay. So we have a lot of very good instructors these 2 weeks. Andrew here. And the first week for this class, for our final class, and Agustin there for the second week, and Gabriel, Sara, Alberto, Bernardo in the other class. So how the school is going to work? So every day we will wake up, come to the school. At 8:30 you have lectures. At some point a coffee break here at this auditorium. If you have your badge with you, you can have some lunch at the university restaurant, okay? Then you come back for the contest. If you don't have your badge, you go hungry for the contest, okay? And then again, if you have your badge, you can have dinner at the university restaurant. And then you go to sleep and you repeat until you are very exhausted in the end of the second week, okay? But it's going to be exhausting, but it's going to be very good, a very good experience, doing lectures and contests every day. This is for the other class. And we're gonna have some other events. Okay, so this is every day except Thursday and Saturday. Sorry, and Sunday. On Thursday, we have sponsor day. So the first Thursday, we are going to have a coffee break and take photos of you from teams, individually, country. You can bring a flag for your country if you have one. And if the weather allows, a group photo of everyone in the school. We're gonna have a talk by Canals, then we have lunch, and then we have an event from BTG Pactual. On Saturday night, the first Saturday, instead of going to university restaurant, we are going to have a pizza party offered by Huawei, and a karaoke here on the auditorium. Okay, doesn't fit everyone in the auditorium, okay, but not everyone's gonna want to participate in the karaoke, so it's okay. And the other Thursday we have coffee break and photos again, a talk by Neon, lunch, a talk by Institute of Computing, Unicamp, coffee break here, and we are going to come here to talk to you, me and Carlinhos, about your experience in the summer school and the ICPC in general, okay? Like how it's going to, what's going to happen in the Latin American finals. Yeah, maybe some spoilers. Okay, it's to hear you, get some questions and so on, and we're going to have this for both classes. Okay? So, just to finish, I want to thank our sponsors again. They are what made possible this school with so many people. So I ask you to go to their events, show appreciation for them, so they keep sponsoring the school and the school can happen every year. I want to thank the Institute of Computing, which allows us to do the school here. And gives a lot of help in many ways. Brazilian Computing Society, which provides financial support and a lot of other support for us. The other organizers, their part which helps organizing the school. The staff members, which you see around there, serving coffee breaks, leading you to the restaurant and so on. And you for coming to the school in the summer instead of staying home, resting, playing some games or something like that. Okay, so please join our Telegram group. We have some announcements there. I know a lot of you are already there, but please join if you didn't already. We're gonna have all announcements for the school is gonna be there. And please follow us at the Instagram. Where we are going to put a lot of photos during the 2 weeks. Okay? Carlinhos, you want to say something? No? Okay. Okay, so thank you. We are going to start.
Thank you very much, Ragnar. Hello everyone. Bom dia. Buenos dias. Hello. Hello. I'm really happy to be here with you. So the first week. Oh my God. Okay. Is that better? Yeah. Okay. So the first week of our summer school. It's cool that there's summer here because there from where I come. It's a very, very cold winter, like -20. And our days on the first week will be arranged like this. As was shown on the diagram, we will be coming here at 8:30 every day. We will be having a lecture. Today's lecture will be a little bit shorter because we are starting a little bit late. Also, we will have to fine-tune our communication because I am not an English native speaker, you're not an English native speaker, so if you don't follow me if you don't understand what I say. Don't hesitate to ask me to repeat. Our common goal is so that everyone understands everything mostly and gets most of this camp, okay? Also, after that, we will have lunch, and after lunch we will have conference. I, together with my friend Oleg Krystenko, whom some of you might know, have set up a special site for you for the contest. You must have received logins and passwords for that site, did you? If you didn't, we will arrange that after lunch today, or during the lunch maybe. All of you must have received 2 logins, one for the team and one for the person. You can choose, it's your option. If you're participating in the team this year, going to Latin America Championship, plan to go to World Finals, training like this, it's okay. If you feel your team is like, maybe will be changed or whatever, you can, or maybe some of you want to try it. Right. Individually, it's not a problem. Also, we will have so-called upsolving after the contest, after the dinner, in the night. If you do not have enough time during the contest, you can also solve more problems. And this upsolving will be up indefinitely. So after the campaigns, when you go back to your countries, you can continue your upsolving until, I don't know, until Alex's servers go down. I don't know if it would ever happen. So, we will switch to theory now. The theory will not be directly connected to the contest. So the contests are just like nice problem sets from different Russian and Northern Eurasian competitions that were not published on Core Forces training. So you should not have seen those problems. If, or I don't know, whatever reason you have seen, please don't hesitate to contact me after the conference starts. We have some backup program sets for those who have seen that, but I am 99.99% sure you shouldn't have seen that, because we didn't publish them anywhere and you're not from Russia. Okay, so the difficulty of the contest, it gradually increases. So if at some point you feel that it's too difficult for you, for the last 2 days, we will have 2 alternative options of a little bit easier contests. So if you would feel that you are not making progress with these contests, they are too difficult for you, then for Friday after the day of after Thursday, on Friday and Saturday, you will have a choice of 2 contests. So the one, the harder one and the easier one. Okay. Now about the lectures. We will have 2 sessions of 1 hour and a half for the lecture. The first one will usually start at 8:30 today, starting now. We will have some coffee break between them. We will cover some topics which I think are essential for qualifying to World Finals. We're going to do them. We have, I was preparing topics based on what we usually teach our students in preparing for contests in Russia and other countries. But of course, some of the topics may be familiar to you, some of the topics may be not familiar, may be difficult. If the topic is familiar to you, it's the option for you to see from the other side, to see some maybe alternative presentation, because I, long time ago, beyond it, Latin America, like I was teaching this 7 years ago, so most of you probably didn't. Nobody of you did that. So this will be useful. And the set of topics, of course, also. Okay, so let's start today, and our today's main topic. Let us arrange who is making the record. Let's arrange. No? follow the another lagoon. I just wanted to check what is visible on the camera, but okay.
I think
Only this one.
I think this is right.
Okay, let's do that. So our today's lecture is data structures and persistence. So this is the first topic of our summer school. So we will start with the reminder about segment tree. Of course, I think most of you should know this, but if you don't, I will remind you. Or then we will look at the general concept of persistence. Persistent data structure actually is data structure that stores all of its states. So if you modify this, you can roll this back, you can undo, and you can also create some multiple instances of the same data structure with different set of changes. And all of these versions you can access and modify sometimes, and use this to solve some problems. So we'll see some general setup where it helps, and we will also see some particular problems where it helps. So these two are the most important. From inside the segment tree, we will also talk about scan line technique that is widely used in some two-dimensional programs. So that's the plan for today. That are very quick, like sketch of this. So we will go now to some details. First of all, are you okay with understanding me, or should I speak more slow? Slower? Faster? It's okay? Okay.
It's okay.
Okay, now please raise your hand if you have used at any programming contest, on-site, online, bootcamps, whatever, segment tree. I'm really happy to see that, because this way we have a chance to fix our lecture. Okay, what is a segment tree? I will briefly, just to set up our connection, I will briefly repeat that. So the segment tree, we have an array of data, say call it A, equals from 0 to n minus 1 like this, and you will have some wires on its segments. What is a segment? It is actually a lie that we are going to be talking about segments, because we're going to be talking about half intervals, so like left included, right excluded. So we want to do something, whatever, with this segment. Our data structure segment tree allows us to arrange this data in the array A in such a way that whatever segment we would like to process, it is divided into at most logarithm and vertices of the tree. So usually what you do, you put the whole array in the root of the tree, and then you divide it into halves, like from 0 to n divided by 2, from n by 2 to n, and so on. And the leaves of the tree correspond to the elements of the array. Whenever you have some query, okay, let's suppose you have some query, for example, the sum of the elements in the array. You do the following. So every node of your tree stores the value of this query for the segment that it corresponds to. So the root of the tree stores the sum of all elements in the array. This is the first half, the second half, and so on. So every node of the tree has some data value. Let's call it V. That's value that corresponds to the query you want to address. So let's start. Now, how to store this tree? Usually, when we're working with segment trees, you are storing trees packed into array, like some other data structure also uses, called binary heap. Binary heap is very popular in the algorithms and data structures courses, but it's in the contests now. I think it's almost never used, but okay. So the storage of the array looks like this. Let's call it tree. So you put the root to the index 0, and if you put some node to the index I, you put its children, its sons, into 2i plus 1 and 2i plus 2. This is 0 index. If you have all style 1 index, I don't know if anybody teaches this in Latin America now, then that would be just 2i and 2i plus 1. But we will use 0 basically. So if you pack it like this, your tree takes at most 4 times n the size of the original array. Actually, it can be optimized a little bit, but that is not our goal now. So whenever you make an query in the tree, you make it like this. I will write this code down, not because I think that you don't remember that, of course, I believe that you do, but because we will need to modify it in some way after we're switching to persistent data structure. So we will need to have some basic. So what does this query operation, what parameters does it require? Usually you pass the following parameters. You pass the index in the tree, say I, which is corresponding to the node that you're making a query. Then you have the borders of the segment that this node corresponds to. Let's call it arc. And next, the query parameters. The query parameters in our case are the ends of the segment that you want to calculate the sum. To differentiate from the segment options, we will have. So any operations on the segment tree actually follows the same pattern. We will write it down like this. So the first question you must ask yourself is, where am I? What do I mean? You process it differently for different nodes of the tree. Actually, each node can have 3 options. It can be completely its segment, the segment corresponding with this node, can be completely inside, completely outside of the query, or on the border. So, where am I corresponds to understanding which of these 3 cases takes place, and since there are only 2 borders of the query, at most 2 nodes will be on the border. There can be other cases that both borders are inside one node, for example, for the root. It also corresponds to the border case. So this, after you find out where are you, where am I? The second thing is to go to children. So inside where am I? If you are completely inside the segment or completely outside of the segment, you can immediately understand what to do and do it. But if you are on the border, you need to go to the children. To go to the children, there are 2 actually types of queries. Just read-only queries like this, some which only reads some data. And there can also be modification queries that change the data in our array. if you make modification query, then after going to children and returning, the data that we store in our node can change. So the third operation that you should do is to update your sample. Update current. So this is the general pattern of any query operation, no matter reading or modifying for the segment. So for the sum, well, actually, where am I is almost always the same. So how do we check where are we? So if we are inside, like inside means that query left border is less or equal to L, and the R is less or equal to 12. If we are inside, well, usually we just return the value that we're storing here. In this case, like this. When we have only one thing in our segment tree, we just usually we can omit the structure and just return T of I. If we will soon store some more information inside the node, so we should return. So outside is also easy. So outside, either the right border of the node is to the left of the left border of the query, or if we have like where we write let's equal to L or R where we left, we are outside. But for the sum query, in this case we usually just return that this node doesn't count into our query, so in this case we just return 0 for the sum. We have some other queries like maximum we return minus infinity, I think. So, and if we are not outside on the side of the border, we go to children. So we like result. We move to the center. And we go to result is plus and we are returning this. So no need to update ourselves because this is not a modification. So if you understand this pattern, you can whatever super difficult operation you have. Maybe you have some like dynamic programming and you have the segment tree of calculations on your segments. You have like table of 4 to 4, whatever you are storing there. If you understand this pattern, you can also always make simple code similar to this one or whatever query. Now, before we are moving to the main topic of persistence, another thing that we need to understand is delayed operation. Let's consider our array, and suppose that we would like to make some operations on segments. So like you add the same value to all elements on some segment. So this is modification operation now, not query operation. So what you would like to do, following the general concept of the segment tree, is that you want to split your segment of the query that you are modifying into logarithm smaller segments inside the nodes of the tree and do something with them. But what would you do with them? The answer is you would put a special mark in this node that tells that we would like to add some value to all elements of this segment. This is the modification flag. Let's call it, I don't know, modification. So when you are making queries, then you would need to somehow take this modification into account. To make it easier, the main idea is not to use this modification directly, but just to say that actually what we want to update every element of this segment, add this value to this element. So, but if we don't need some value, then why would we update that? We don't need this. So it's kind of lazy operations in some other programming language. So you only update some value when you need it. So when you are going down the tree in the query operation, if you are going through the node that is that has some modification flag, then you just put those modification values, push those modification values down your tree. So this general pattern has new 1.5 when we just push, delay modifications down. That is working. Let's see. Again, there are a little bit different styles of implementing this in code. I will give you one style if you have already learned about this in your other studies and use different style you might consider, because what I will tell you the difference, and what I am teaching now for me is less bug prone, so there are fewer bugs, especially in difficult operations in symmetry. So how would you make this modification? Let's see. So we have this modification here, and this says, okay, 3. It means you must add the 3 to all elements in the array from L to R. M is bad, yeah, but you know. Let's call it some other letter. A, L. So, what does this mean? If we have here some value, for example, that means that this value actually we should add 3 to all elements in this array, so we should add to the value of this array here R minus L times A, correct? So the actual value is that bigger than the value stored here. So what I usually do is I store this value in this particular node already modified. So you store this already modified, so when you look at the node, sometimes in your code, you will see that. You just process some node inside where am I, and you should look at, or update current node, you look at its children, and you don't want to mess with your children's modification flags. So you would like to only look at your children's values, so your child nodes. So this value should be already correct. Like, I don't know, 15. So this already includes this. And when you make push delayed modifications down, what you do? We have two children. It has some A from A to M and some B. And it has some A. Its segment is from M to R, and it has some value. So what should you do? First, you should add this value to all elements of the segment. For this node, it's the same as to add this value to these elements and to these elements, correct? So you say t times I plus 1 with A plus equal to our value of A. And same for the right, no? But, okay, so the value is now incorrect for those children because it doesn't know about this modification yet. So what we also need to do is we need to add to this value times the length of the segment, like m minus m. So here is the subtle difference. So if there are two ways to do this, either you already have this included in this very vertex, this very node, or you don't. So if you didn't, you would here modify this node itself. I find it easier to code if you already include this modification in your current node, because when you look at your children for whatever reason, you don't need to look if they have any modifications. So the general rule here is if you visit any node, its value is correct, its modification flag is neutral, no modification, 0, and its children values are correct if it has any children. Of course, there can be a leaf if it has no children. So after you do this to your left son, you also do this to your right son, and then you change your own modification left to 0. So this is the general code of pushing delayed modifications down. You update modifications of your children. You update the values of your children because you want them to be already correct. And you clear your modification. That's usually encapsulated in push operation. That also takes all these parameters, maybe not wire parameters, because it doesn't require also ILR, and it makes all these operations. Is it clear, or should I give more details? Okay? Okay. So, if you do it this way, if you modify it this way, then here we would have like ILR. So this is 1, where this is 2. Oh no, this is 1.5. 1.5 push. This is 2. Go to children. Update ourselves is empty here because it's not modified, and returns. If let's see, so not some but add the 2 set. So it's the same, but we also need the value to add. So if you look at this pattern, it's just very easy to modify. So if we are inside, what do we do? We update our modification value, like ti plus equal to n. We update our real value. Corresponding to our method of storing our result already updated. So that's it. Return. If we are outside, we just don't do anything. In the other case, we make push. We must make push before going to children to make sure that all above the current node is okay. Then we go to children. Not update it, just 2I plus 1 ln and so on, and two others. And here our part 3 is not empty, so we make the real modification. We have to recalculate ourselves, and this is where we have the benefit of our way of storing these integers. We just write t of I dot value to I plus 1 dot value plus 2. These values are already correct, even if it was the case like that. So, at this point, I think that we have synchronized our implementation of segment chain. If you have any questions so far, please ask. If it's not, we will move on. Okay? Okay, so I should only use this board. Yes? Question?
Why do you want to store this ti.a in part 1?
Why do I store this?
Yes.
Because I return here. You see, if suppose I have made modification to this node. These nodes, all of its subtrain, don't know yet about this modification. They will know this if they are asked. If we query and any of these nodes is visited, you should know about that. So we store this and we push it down like here. When we go through this down. If we don't go down, it will never be pushed. If we go down, it will be pushed down and updated. So it's called delayed operations or also lazy operations. You don't do what you don't need to do. Question?
Is why not this plus up in so instead of ti.a why not?
Well, it's not equals, by the way, it's plus.
Yeah, it's not.
What is there? Yes. Thank you. That was incorrect. Any other questions? Okay. Now then, I was asking a question, but nobody did answer. Yes, so I should only use this word. Then I use some others. Okay. No problem. Before moving to persistence, I would like to give you some example of problems that can be solved using segment tree with such called scanline technique. Okay, so we will first consider two tasks. Task number 1. We have a two-dimensional with a point. And we have queries which are rectangular. Queries which are rectangular. The question is for, well, there can be multiple questions asked in such setting. One simple question is, for every rectangle, how many points are inside? There can be other questions like which point is covered by the most number of rectangles, or which rectangle contains as many points, maximum number of points is the same as this, how many rectangles are covering each point, and so on. So in this setting, there are many points. Problem number 2, we're going to consider, before moving on, is rectangles, and what is their total area, the sum, the total area of all rectangles. So these two problems are classical problems for scanline 2D that we will now consider. So let's start with this problem. Let's first consider its one-dimensional alternative. So we have like a line, we have points on the line, we have segments, and for each segment we want to know how many points are there. How would you solve this problem? So let's walk along this line from left to right and keep track of how many points are there. So how many points have we already seen? When the segment starts, we say, okay, this point that we have already seen will not be in this segment. So the current balance for this segment is minus the current number of points. So if you add the current number of points to the balance of the segment, you will get the number of points in this segment so far, because after you walk on, you will see this. So this segment has balance of 0, so this first point is inside this balance of 1. This segment at this point has balance of -1, so it has 0 points. Our current number of points is 1, and this balance is -1. So now 1, 0. You see this point, so we now have 2 points. This segment has both of them 2, and this segment has only one of them because it is adjusted by -1. So when the segment is over, when it's ending, the number of points inside this segment is just known. It's our current number of points minus its balance. So this is called events on the line, or some point. So you go from left to right and you have events. There are 3 types of events in this setting. The segment starts, the segment ends, and you see the point. So when you see the point, you say, so here we have like ends of I is minus current. If segment number I starts, so this current plus this. Okay. So let's move back to the two-dimensional problem. In 2 dimensions, the problem is that points also have y coordinate, so we cannot simply count the number. What will we do? Let's project all points to the y-axis, and sort them arranging to this y-axis. So this will be position number 0, position number 1, 2, 3, 4, 5. So, right? Is that if 2 points have the same y coordinate, it doesn't matter. Actually, you can make them separate copies of this y coordinate, or you can make one. I would make the common, so like coordinate compression. And what we're gonna do? We're gonna store in the array 0, 1, 2. So like n-1. How many points with this y coordinate we have already seen? So it's like current here, but separate for each y coordinate. When we see the point, what should we do? We should increase this value by 1. because we have one more point with this whiteboard. Now, how do we process rectangles? When we see the left border of rectangles, or a rectangle, let's check the part of the array that corresponds to this rectangle. It can be easily found using, for example, binaries. All the points here counted so far are not inside this rectangle. So we, like we did here, subtract from the sum on this segment from the answer for this rectangle. Well, the answer is not yet known, but we know that it will be actually smaller by this value than the sum that we will see, as you, I guess, have already understood. When we see the right part. Sum from bottom. And when we see the right border of our rectangle, right edge, we, this is left, this is right. We add for this sum. And for counting the sum on the segment, we already know what to do. This is our segment shape. So, let's see what is the complexity of this solution. Complexity. Understand complexity of this solution. Suppose we have n points. Let's say n points. N rectangles. What is the time complexity? Well, first we need to sort all this thing down, so it's n plus n times logarithm of whatever again, plus n. And then we go into all of those, and we're making queries for this segment tree, so again, n plus n events, and each event is processed in logarithm of what? Of n. So this is smaller than this. So sorting is the worst part asymptotically. Actually, of course, queries in segment tree are more expensive, so sorting will not be an issue here. Queries. So answering other questions. How would you answer other questions that we have discussed in this setting? For example, the point covered by the maximum number of rectangles. How would we answer that? Here we have different things to store. Let's again, if you have such two-dimensional problem, good first step would be to look at the one-dimensional problem. If I was teaching IY class, I would even say that there should be such subtests, yes, but in ICPC there are no subtests, so this is only for our first investigation. So we, in one-dimensional, point covered by the maximum number of segments. We see, now we have, in the previous session we were counting the number of points seen so far, now we're counting the number of segments open so far. So when we see the segments start, we say count of segments plus 1. When we see it end, number of segments minus 1. And the point, we just know the number of segments it has been covered by, and we relate the answer with this value. If it's better than our current norm maximum, we update. So in two-dimensional setting, again, this time let's do a little bit different. This time no, not different, absolutely the same. We have, again, y coordinates of our points. And when we see the rectangle, all points at this segment are now covered by one rectangle more. So we make +1 update on the segment. We know how to do this. We have discussed delayed operations. When the segment has -1 on this segment, and when there is a point, we just query at this point how many segments are covered in this coordinate right now. So this would be, and the maximum of these values is the answer. Okay. Okay, now let's move to the final problem of this part. The problem of finding the total area covered by rectangles. Again, let's start with the one-dimensional set. We haven't forgotten yet that we are that we have two-dimensional setting. The first thing to try is one-dimensional. I would say that it can be extended more. So, like, when we have three-dimensional setting, let's start with two-dimensional setting. But unfortunately, it doesn't easily generalize to more than two dimensions. There are some problems that can be solved in three dimensions with a similar technique, but almost every such problem has some trick. So there is no general two-dimensional idea that we can generalize. Two-dimensionals come play. So, okay, but here, let's get back. So we have like points on the line. No points, only segments. We have segments on the line, and our question is to calculate the total length covered by this segment. Easy. We count, like in the problem, how many segments cover each point. We keep track of how many segments we have open now, and when it comes from 0 to non-zero, that is the left part of some covered segment. When it goes from non-zero to 0, actually from 1 to 0, this is the right part. So for all, and if we sum, we see sum Ri minus Li equal to sum of Li minus sum of Li, yeah? So if we do it like this, we can see that every time the number of segments goes from 0 to 1, we subtract our current coordinate from this final result, and every time it goes from non-zero to 0, we add this to the total answer. How would we do this in 2 dimensions? There is a small trick actually. Let's split our plane. We call plane 2. Horizontal stripes, like this. By all possible y coordinates of top and bottom of the rectangle. So for each stripe, this is a one-dimensional problem that we have just discussed. So for each stripe, when we go from 0 to 1, we must add, we must subtract the current x coordinate from the answer. Now, since it's two-dimensional, not simply the x coordinate but the x coordinate multiplied by the height of the stripe. And every time we go from non-zero to 0, we add current coordinate multiplied by the height of the stripe to the answer. So the question is, now how can we use segment tree for this task? How can we actually see for the stripe if it goes from 0 to non-zero, from non-zero to 0? There are several options to do this. You can push down to do exactly what I say, but there is a small trick for this particular program that helps with a very simple segment tree. It is using bounding box. So instead of counting the total area covered by segment by rectangles, it is a little bit easier to count the total area not covered by the rectangles. Why? Because for covered we have some positive number which can be 1, 2, 3, 1000. And for non-covered it is always 0. So counting the number of zeros is easier than counting the number of non-zeros in some sense. Of course it's the same, as you can see, but now you see that it's the same, but before I said that, it seemed like not the same, yeah? So let's put some boundary rectangle, which includes all of ours. And for the implementation, to have an easier implementation, it is even better to have it a little bit more than the bounding box. So not the minimal x, maximal x, minimal y, maximal y, but plus 1, for example. It doesn't matter, but it helps a little bit, so that there will, for every horizontal and every vertical stripe, there will always be 0. So, and now what do we do? Again, we have the segment tree of these stripes, and we want to have the sum. The value stored in segment tree is now a little bit different. It is the total area, the total height of all stripes that are 0. So we have the value. We would like adding a rectangle. We are adding 1 to this value. So and the additional value on each node is total number, total height of zeros. So when we are planning our solution with segment tree, we need to understand 2 things: how to combine the data from children, and since we have group modifications, we need segment updates, so we need to have this lazy flags. We need to know how to push the information down. But here we have here it is quite easy. So combining information from children. So what should we store in this value? This value is we say covered by or not covered by. So what I would store here is the minimal number of rectangles covering some stripes. So there can be other options, but I would use minimum. So minimum is okay. For minimum we can add, we can subtract, and we can check if minimum is 0. 0 is the smallest possible one. So we have minimum, and we have now 12 zeros. So minimum is easy to update, number of zeros is easy to update. If minimum is 0, the number of zeros is length of this segment. If minimum is not 0, the number of zeros is 0. No, not exactly. So if minimum is 0, then if when we are combining, if both children's, if minimum in both children is 0, then number of 0 is sum of these values. If one of this is not 0, then only from the one which is 0. And yes, and if it's not 0, then it's always 0. Okay. So at this point, I think that since we started late, we will make. My suggestion is the following: we make a coffee break now before moving to persistence, and then we will get back at 10 a.m. We will have 1.5 full class processes. So okay, now let's make some coffee break. Thank you.
Thank you.
You know how to take action.
Aumentar um pouco, né? Tá baixo.
Vou olhar baixo.
I would like some small correction to what I was saying in the last
Ele fica
minute
estourando.
of the
Mas tá
first
bom.
part of our lecture about
Mas tá bom.
this technique of counting zeros. We're discussing with some active participants of our camp, and we have decided that it should not be number of zeros here, but number of minima. Why? Why? The answer is because you cannot update number of zeros when you subtract. When you increase by one, it's okay, but with zero, it's not zero. But when you subtract, you don't know if your minimum, well, you know if your minimum has become zero or not. But if it has become zero, you should now count the number of those zeros. And if you didn't know the number of ones before, you should know. So what you do, you store the minimum and the number of minimums. Updating minimum is easy. Updating number of minimums is also easy. Even easier actually for me with the number of zeros, because you just, if those both minima in our subtrace are the same, you just sum the number of minima there, and if they're different, then the number of minima comes from the node that has the actual minimum. Okay, so having said that, let's move on to the second part of our today lecture, persistence. What is the persistence? Well, initially, the concept of persistence was developed for databases. So you know, when you have a load database, and you have queries which update your data, which wire your data, which come at a speed, the update query should not stop the function of database totally, and other queries should be still able to process. And so the authors of database engines had to come up with some solution, and they came up with the concept of persistence, which allows you to access not only the last revision of your data, but also to some previous revision. But now we will be talking about how persistence is used widely used in programming computations data structures. So the main idea, well, there are actually 4 levels of persistence so far. The first one is partial. Partial persistence means that you can read any version of your data structure, but you can modify only the last one. So you have like a single line of revisions, revision 0, revision 1, revision 2, revision 3, and so on. And you can access any revision, but you can only modify the last one. We will not actually see partial persistence today. For our data structures that we will discuss are so easy, so simple that you can make full persistence for them. But for some complicated data structures, if you're interested, you can read some books or lectures on persistence. There are some quite complicated structures, or if you want some improvements in complexity, you can sometimes benefit from partial persistence. You cannot modify earlier individuals. Full persistence, second level. You can modify any version of your data structure, and you can query, read any version of your data structure. So you have some initial revision, 0, and you can modify whichever you like, getting new revisions. So the revisions in this case form kind of a tree, and the new versions can be added to as a new leaf to any part of the tree. This is full persistence. You can ask me what can be more than full, but actually you can, because, for example, some operations on some data structures combine several instances of a data structure. One good example is a tree or a functionalism tree. Does everybody know what a tree is? Who knows what a tree is? Tree. Oh, not everybody. Okay, most of them. Okay, that's fine. If you know the tree, you know that you can split and merge. And merge takes two trees and creates a new tree. So, if you can combine two versions of the same data structure that you have created at some point, this is the third level. Sorry, I forgotten its name. Forgotten its name. Is that called? Yeah, remember I don't. There's a word that is only used in this context, so I'm sorry. Okay, and now so in this case, this tree is not a tree anymore because you can combine different versions of this same data structure. And one funny thing that you can do, suppose you take a tree of one vertex and you combine it with itself, and you combine it with itself, and you again combine it with itself, and how many virtual nodes would the nth revision of this tree have? 2 to n, yeah? So you would have the giant tree, which has a 2 to n node. We will discuss this a little bit later. And the fourth level of persistence is called purely functional. Actually, this is not these three were the levels of say interface size. So I mean that the interface of the data structure changes. In this case, you have modifier for the last revision. In this case, for every revision. In this case, you have multiple instances of the same data, revisions of the same data structure to be combined in one operation. But purely functional is the level of what you can actually do. And in purely functional, every memory cell in your implementation, every field in your structure is one at most can be assigned a non-default value at most once. So, assign once. assign once means that your data structures are automatically persistent because you cannot ruin your previous revisions. You cannot assign anything new to its fields, so you will not be able to damage them. So you can always access previous versions. However, of course, there can be some other implementations that do not use purely functional, that can give interface of partially or fully persistent data structure, but actually reassign something does. Okay, let's start with the simplest data structure, which will become persistent. It's persistent stack. Persistent stack. Let's remember what is a stack. Stack is easy, yeah. So you can push and you can flop, and it's last in, first out. Well, let's make state persistent. What does it mean? What does it mean? How can we make our data structure persistent in our code? So let's do this. We will make we will try to make purely functional data structures. It is quite easy to think about this. You can make all fields in your structure that you are storing the node as constant. So you can only them assign when you construct the node. It is from the point of view of programming language C++, it's not always convenient to do so. You sometimes want to calculate some rather complicated values to be assigned, some complicated expressions. It's not convenient to assign them when you construct, pass them to the constructor. There are some programming languages, like functional programming languages, Haskell or Camel, that have special design built so that it is convenient to do this, to do assign once structures. C++ is not such language. It is not always convenient to write it. So you can make it not syntactically but semantically. So you do not put const in front of every field of your structure, but you never assign new value other than when creating the node. When creating the node, you may make some calculations after you create it and assign, but not reassign it later. So here, what is the stack? What is the most traditional implementation of the stack? You will make, it's like std vector. But it is difficult to make it persistent because when you for example, pop something and then push something new, the old value is lost. So you cannot restore the old version. We will use some kind of list for this. So we will have some node. Actually, all our structures, including a persistent array that we will also consider, will be node-based. So we will have a node. What will this node store? This node will store first its value, and also for the stack, we want to know the node under us, the next. We don't want to know the node on top of us. We will see that if you want to know both the node under us and on top of us, it's not. Okay, so how do we make push? How do we make any the interface of any persistent structure? Since we have multiple revisions, what we cannot say when you are usually working. For example, you make vector A, and you work with that. You push, you pop, because you have one vector and you have its current revision. But when you're working with persistent structures, you have multiple revisions, and all of them are accessible in some sense. So what you need to do is you need to store all these revisions in some way. Usually, you would like to give those revisions indexes, like the revision number 0, number 1, number 2, and so on. And when you make any modification, you create the new revision and give it the new number. And what you do is store all these revisions in an array called revisions, for example, and the element number I is in some sense the reference, the pointer to the entry point to the data structure of this revision. So for the step, what is the entry point? The topmost element. So if you know the reference to the topmost element, then you following this next pointers, you can, for example, print, analyze, do whatever you need with a constant. So this vector would actually be no abstract. It would contain this. If you don't like pointers, I know that you might not like pointers. There can be two reasons for that actually. One is you just don't like them because they can be null, and that will be a null pointer not exception, but whatever C++ would do if you reference the 0 pointer. And the second thing is because when you're working with pointers, you're actually delegating your memory management to the general C++ runtime system. You know, C++ standard library is a very, very complicated memory manager. When you write new in your code or delete in your code, it must have some way to have information about free memory, chunks of this memory. They have actually, if you read the reference, quite tricky data structures that are stored exactly in that free memory, that store information about that free memory, and when they give it to you, they like delete it from their free memory data structure and give it to you, to your program, and then back. And so new and delete are not so very cheap operations. And if you're tight in time, you might want to get rid of that and use your own primitive memory manager, especially when you only have one type of object that you allocate. Your C++ compiler cannot guess that you only will have single memory, a single type of chunks that you want to allocate. So in this case, here you can have like vector of int, and you have another vector of node, your memory. And this, you would probably, it's programming contest, so you would probably never delete anything. And if you do not delete anything, your pseudo new, you just create new node, and it's indexed in this vector, you just push back, and the index of this back element is your pointer to your node. So in this case, instead of node star, you always write int, and you have one with your manual memory management. I will now give examples of code that uses real C++ pointers, but you can keep in mind that sometimes it would be, the code would be a little bit easier if you do this. The code would be more, I don't know how to say, dirty, maybe, because instead of like node x, you will have to write name of n.x, which is not so easy to perceive. So maybe, but sometimes, unfortunately, we have to go to manual memory. Okay, but let's try using actual point C++ pointer. So, what is our initial revision? Our initial revision is 0. Well, usually it is empty stack. So what is empty stack? It's null pointer, yeah? So it doesn't have any null. So when you push, you get your node that you want to have, like that you want to push into stack, and the element that you want to push next. So usually push operation doesn't return anything. Why would it return anything? It pushes and it's okay, it's there. But in our case, when we are working with persistent data structures, when we are pushing it, when we are doing any modification to our data structure, we do not modify that stack. We create the new stack, the new revision. So we should return it. Well, okay, how do we return it? Let's see. So we have this stack like this. So we must create new node. New stack. It will be new node. What will be its fields? The value is just what we are pushing, X. And the next, what is under this unit? Exactly the stack that we are pushing in. Yes. And that's it, we return. New stack. So this way we create the new node. And now about popping. So we are popping from stack S. So what should we return? The first question. First, we would probably like to return the new value, the popped value. We're popping for something. So the popped value is stored in S value. And but also when we make pop, it is also a modifying operation on our stack. So we should remove this top node from the stack. Now the new stack is the stack under it. So what we are returning here is actually a pair of the value. Let's say it's int, it doesn't matter. And the new revision of our stack. And here it's also easy, so we return as value. And the new stack after we pop this is exactly what S next is pointed to. Okay. Note that if we were using this list implementation for ordinary stack, it would be our temptation here to delete S before returning. We would store this pair to some temporary variable, delete S, and then return, because we would not like this memory to leave. But in persistent setup, we do not need, we cannot, we should not delete S, because it is our previous version of our stack that we should keep for a future record. So we do not delete S. And when making calls to push and pop, actually, since I've told you we would like probably to keep this revision for some reason, we're doing like revisions push back, push from some revisions number, whichever revision we need to push into, and whichever value we need to push. And when we're open, it's a little bit more complicated. We need to get this value in the revision into from pop. and store this revision into our revisions. I think that maybe some C++ 31 or something can make some after lambda after and get this in one line, but I wouldn't do that's the type of program. Okay, so what do we have got? We have got purely functional implementation of stack. Because we do not ever modify, we never write something like node value equal to whatever or node next equal to whatever. Since we don't do this, and we do not delete nodes. So since we do not do this, we can never damage our previous revision. So we always have access to that. Let's also see how this actually looks in our memory. And you can see that it looks exactly the same, just the arrows are in the opposite direction. We have actually zeros version pointer. And we push something here, get this version, we push something, push something. When we pop, we actually, in some sense, save memory, because if we pop from this and get the new revision like 4, 4 is equal to 1. If we push them to 4 from like 5, 6 to 3, we get it. So now when we have, for example, we take revision number 6, it is storing whatever we pushed to get revision 1, then 3, so its stack is a canonical example because it is stored as a tree, and this tree is in some sense almost isomorphic to the tree of revisions. If you only do pushes, it will be isomorphic completely. If you do pops, it will merge some versions into the same node, but it will still look like this tree if you only consider pushes. Okay, now let's move on. Our next data structure that we will make persistent. Question? You don't copy anything. See? You just create your node when you push. We will do copy nodes in the next example. In stack, we don't need copy nodes. Yeah, the question?
Pop receives 2 arguments.
Pop receives only 1 argument. From where do we pop? In here, yes. It is correct. You do not pop X, you pop this. Yes, yes. Okay. Other comments or questions? Okay, so the next thing we're gonna do is we're gonna have, in some sense, 2 in 1. We will now have segment, persistent segment 3. That's okay, it will be not that easy, more or less harder than stack, but easier than anything else. But we will get almost full free, not exactly full free. We will get persistent array. Our persistent array will be a persistent segment tree with no operation. So the operation can be any operation, because array, what is array? Array is a data structure when you have only query elements for read and elements for write. So if you make whatever segment tree you like, I don't know, minimum, sum, first element, whatever. If you only query single elements, length 1 segment, it will behave like an array. So in this sense, if you want to make, if you have already persistent segment tree, it can be used as persistent array. And now, if you look at all other data structures that you are implementing in your code, you will see that most of them actually use arrays. Well, yeah, they will use most, maybe vectors with pushback or something, but if you ignore that and make a max possible length initially, then it's array. So, like joint set union, circular queue, whatever, heap, whatever else, whichever you do, if you store it inside an array, you can then make it automatically persistent with some cost, not absolutely for free, but with some cost, but you can make it persistent using persistent array. And this is a trick which is which works almost all the time. There should be some really tight and time limit problem that this trick doesn't work. It's a persistent data structure, but you cannot use segment tree based persistent array. Okay, so let's see if it's such a powerful thing. Let's see. So, let's see, what is a segment tree? Let's draw an example. I will draw an example of a segment tree for minimum no loop operations. For an array of length 4, segment tree for minimum. So suppose I want to change some of its elements, for example this one, from 2 to say 5. Let's try to make it purely functional. What I do, I take this element 2 and want to change it to 5. How can I do this? I cannot change. So the only thing I can do is to make the new node put 5. Okay, now let's take a look at this node. It has 2 children, this one and this one. In the new revision of our segment tree, its left child has changed. But you cannot reassign left child for this node because you do not reassign anything. And also, since the new left child is 5 is greater than its right child 4, so the new minimum value will also change. It will be 4 now. So again, the only thing you can do is to make the new node its left son of this. Now what about its right son? The right son of this node didn't change. So you can, as we did instead when we wrote open, going back to the node that we already have, it will never be damaged, it will never change, so we can go there second. The same here, we have the right son that didn't change, so we can safely put the reference to its right son here. It will look a little bit strange, but it looks like this. So this is our right son. It will be the same as before. Not as before. There is no before in full persistent. There is no time. There is like mix and everything. As in previous revision. And this has minimal also. And now the root node. For the root node, again, the left son didn't change, and the right son did change, and this is a new revision of this right son, and the minimum value is 1. You see that minimum value is the same, so it can be tempting at first sight to keep the root as it was before, because it's the same minimum value 1. But remember that all fields must change. So not only the value that we store, but also children cannot change. So in this case, since we have the new child, we have to do that. So this I don't know, octopus-like structure on the whiteboard represents now 2 versions of our segment tree. If you ignore this picture and look at this and consider yourself as a C++ compiler, and look at this not the compiler maybe run in time, and look at this node as the root of the tree, you will see the first completely read revision of our tree. If you look at this one, even if you don't know anything about the red revision, the previous read, you will see the normal, usual segment tree with 4 elements, like 3, 1, 5, 4. And so now we have 2 revisions, and to create the new revision, we only created 3 new vertices. I had 7 vertices initially, but we only needed to create 3 new vertices for this new revision. And this will always be the case. For the segment tree, when you create the new revision, you only create new node for every vertex on the path to the new value. And there are logarithm n plus minus 1, the height of the tree vertices. You do not need to look to create new revisions of the vertices that are not on this path. The general rule is, this is the way to make a node-based data structure persistence, which is called node copy. Okay. And the general rule is the following. You create the new versions of all nodes from which you can reach the modified one. You that from you can reach modified. And in case of segment tree, classic implementation, which we were given here, these are exactly the nodes that your recursive calls pass through. Because when you go, remember our query function sum or add to segment. They both did what? Let's recall. Number 1, where am I? That's where am I? Number 2, let's fix some numeration. Number 2, push if needed. Number 3, go to children. Number 4, update yourself. So, if where am I decided that we shouldn't touch this node and went up, it's okay. This node needed to be copied. But if where am I decided that we need to change some values, if we are inside, completely inside, then we cannot change. If we make a purely functional, we create a new copy. If we push, we'll come back to it later, it creates 2 more vertices, but asymptotically still logarithm. If we don't have group operation, then push is not needed, so we skip this step. We go to children. At least one of the children will be modified. You cannot have both children outside of the segment of the query, because in this case, our segment would also be completely outside, and where am I should have a return. So we create the new version of at least one of its children, and so one of its children is modified, and we should create our new self, and this our new self will be initialized, and this is the first and the only assignment to its fields, with the correct values that it collects from its children. Okay? So we have this one. So unlike classical implementation of segment tree, we cannot pack this corpus into the arrays. Well, we can pack whatever we want into array, but there will not be such simple rule for is indices of the children. So what we need to do now, we unfortunately, or maybe fortunately, if you like object-oriented programming, create the structure for the node that stores all the elements that you need. So value, maybe some modification, and now we need to have references to our children, like here, nodes, enter R. And our functions that work with our nodes, that work with our queries, now return the new version of our node. Here are some notes about this. There are reading operations. Reading operations do not change your tree, do not change your segment. So reading operations usually do not create new revisions. There, from here, we have two conclusions, two steps of conclusions. But if you have delayed operations, if you have lazy operations, reading operation actually modifies your tree. It pushes and changes the values in the nodes. So reading operations, when I have group queries with modifications, would create new revisions. But the chain of two conclusions is that you don't need those, because why would you need those new revisions? They store the same data as before, just these delayed operations are moved around the tree to get the correct value. If you note that in segment tree, even with these delayed operations, there is no proposed amortization. All operations are truly logarithm and are truly proportional to the height of the tree. All these pushes, they have to be done to be correctly, so that the queries were answered correctly. But actually, if we roll those pushes back after answering the query, you can still work with that tree. You do not need to store these pushes values actually down there. You can undo if you wish. If you just don't do this, why would you do that? But in persistent case, know that not only these three nodes add to our time complexity that we have to create them, but they also add to memory complexity, because these three nodes need to be stored. And when you have push, you also push for every node that you visit on your path, you always create two new children with a push operation. And actually, if you go down to one or even both of these children, then you will create another new version of this child, because it will be modified again, probably. So, one thing that you could do is to delete, erase all those new nodes that you have created in the reading operation, even when you have group modification is delayed. It is tricky maybe to do this, but I know some problems with contests where you needed to do this to fit into memory. It might be easier with your manual memory management, because your manual memory management, how does it work? You store the vector of nodes that you create. So before doing this reading operations, you create the vector of the nodes. So this is its current state, its current feeling. So when you are going to make a reading operation that will make pushes to get the correct result. You'll remember the stack pointer position, the size of your stack of nodes. You create some new nodes here, but they are not needed actually. So what you do roll back to that position. It is easier to do it with your manual memory manager. If you are trying to do this with the actual memory manager of C++, it's not that easy to do. In this case, you could make your own additional stack of nodes, push the pointers to the newly created nodes, also to this temporary work stack, and then delete them using C++ delete function to free the memory. Sorry for this note here, but you should have noted this. Okay, now getting back. So, for example, let's see how the signature and the main contents of the functions that we do changed. Question now?
Yes, got a question. But what happens when you delete those nodes that have the modification that you push, but that push not only move?
No. When you push from here, all three nodes have new copies. Because you cannot zero out push here, modification over here, you do not modify anything. So all the three are new. And they reference down there. And if you delete them, you cannot, if you use purely functional code style, you cannot damage your previous versions. And since you cannot damage them, whatever new things you have created, if you don't need them, you can delete them. Because older things are not damaged. And that picture also shows why is it so expensive to make node copy with root modification. Because instead of copying just this and download the password, you copy this 3 and download the password. You also copy them 3 times more expensive. Not swap. Let's see. Let me give you a code structure for the persistent version, and you will see how it works. So, how would the code structure for the persistent segment 3 look? So, consider again, for example, let's start with update. So, update. Take the node that you want to update now. We used to push to give index of the node, here to pass index of the node as an argument. Now, as I told you, I will give you the example of the code with real C++ pointers. If you use your own memory management, it will also be the index in your array of nodes. Node or node and other parameters are the same. Left, right, while left, while right, and middle. So now update, the previous update didn't return anything. While we some returned while result. But updates usually didn't return anything in our classical segment realization. Now, this update returns the new version of the node. Because you cannot modify the old version, you will damage your previous revisions. So now, we are following this pattern again, just with the only change that whenever we want to assign something to already existing node, we create the new node instead. Of course, if you assign multiple fields, you can create one new instance of node and assign all this node. So, let's see. Where am I is the same. If we are outside, I will not write the condition if outside. If we are outside, we do not make modification. This is our lucky chance to return back our original n because we didn't modify n. If we are inside completely, then what would we do? We would add the r minus l times v to the value and add value to the modifier. You cannot add to the actual, so we create the new norm. And what it has, its value is the old value plus r minus l times v. Its modifier, it's not commented out, is n modifier plus v. Its left and right are the same as for n. And we return this. You see that n wasn't changed. So previous revision is still completely assessed. Okay, so the file side, the fin side, okay. Now if we have to work with the children, our next step would be to push. Push, unfortunately, as I have told you, will modify the vertex, it will create the new value. So what we could do here, since it's update, we cannot leave out the results of the push. So we will need to store this, we will not delete. Modifying operations, we don't, in case of modifying operations, we do not delete our new nodes, we will need them, we will create a new revision. In the reading operations, the new nodes that are created in push can be then deleted because they are not needed after this read. But here we need them, so we could, but this new node that is created in push actually can be reused. We can delay assigning these fields until we return here to update the result and create and update them actually there. So I will not use this information right now, but generally you can save a little bit here. So let's see, push again creates new node. Right. What does push mean? First it creates new children because we will push, but we can again say here, if for example, if node modifier is 0, nothing to add, return n. We can not push anything if we do not modify. If it's not, then we create new left. And we calculate parameters as an ordinary push, those values that we would assign to our actual left sum, but we do not assign it to our actual left sum, but we assign them to our new node. Same for new right. And same for new this node. Yeah? And we return this. So here, we get it back to here. When we make push, we replace this local variable. It doesn't have an ampersand, so we just locally replace it with m plus 2. So after this operation, actually, we have already made some, I don't know, surgery on our tree. So we had a tree. We at ourselves and our children, and we have already replaced this part with a new part that is still referring there, but the flags are now fixed down. And now we are going to go from this copy to the new copy now. So we go to our children. Again, you left is update. Nodes left some. And then you are right some. Like this. So at this point, you should create actually the new node with this children, and so this one is replaced with something, this one is replaced with something. We copy those twice. This can be generally optimized. This node have not been yet used anywhere. There are no reference to this as to this. So if we establish this, if we go, this is why query function is actually a separate level. We can go 2 levels up to just fully persistent level, and modify this very node to put the new left and new right there in the values, because it was not used. It is not used in any actual revision of our data. But you should be careful actually, because it may look to you that you didn't use it anywhere. But for some reason, in segment 3, with such direct recursive implementation, probably you couldn't use it anymore. But in some other cases, in some more tricky situations, you might think that you are not using anything outside of what you do, but you did. So you should be careful with that. But so if you want to stick with the purely function, you need to create new again, even more new node. Third local revision of this node here with the date and return. So this is how the structure of the persistent segment tree looks. It still follows the same scenario, but this time it is not packed into an array, and all update operations return the new version of this one. Actually, reading operations should also return the new version, because even if you remove these unneeded new nodes after reading operation, you still need them inside the recursion so that it works correctly. Other questions, please?
I don't understand why you should do and equal push.
This?
Yeah, it's the same end as the input of the function.
You can make new variable here, but since this end will not be ever used anymore, why not to reuse it? It's local. It's local. You can, if it scares you, you can use N1, like, but do not forget to use only the new N1.
But you don't change it in the tree.
I don't change it because there is no ampersand. Yeah, it's just a local pass parameter, the source pointer. But changing it doesn't change the variable that was passed with this one. And yes, please.
This N1 is just you create it and
Inside push, yes. Yeah.
and you discard it.
I do not well, yes, it will be discarded. So to save memory, if you feel that you can step one side back, two steps back from functional to just completely persistent, you can reuse. So you can not create new node, but fix the points of node. Since you did want it, you're going to discard it. If you would write it in Pascal, you would not be able to do this anyway. But in C++, yes, you can take a risk. And also, I have recalled the name of the third level of persistence. It is called confident persistence. Please, if you are writing notes, you can answer this during your. Sorry for forgetting that. I should have prepared better. Now, did I answer a question or not? Okay. And your question that was a while ago is okay now? Anybody else? Any questions on the general structure updated with the persistence? Let's count the cost. So all the operations are actually still true logarithm n. Just it got, since all big contains some hidden constant multiplier, this multiplier has grown faster. So it's like more costly now, but still logarithm. About memory. The classical segment tree, we have told that uses 4 times n nodes factor. It can be reduced to like 3n, but it doesn't matter. So here we have 2n initially, but every query operation creates new node. How many? Well, all of logarithm n. If we want to look inside this big O, we will see that depending on do we have pushes or no, do we make some optimizations with pushes like reusing temporary nodes or no, it can be from 1 to up to maybe 6 times logarithm n new nodes for each operation, query operation. So the total memory is 2n plus number of queries times 1 to 6 times logarithm n. So what I've said, this segment tree can be used as an array. Because if you make any operation, well, the fastest like minimum or sum or even whatever, one interesting operation is L times L is L. This, or you can use L times L is R. You just need, it can be tempting to say L times R is 0, but it's dangerous because it's not associative to that. So you should better avoid that. Maybe this is okay, minimum or sum, whatever. Then you, if you only address separate elements with your queries, it's going to be like array. And after that, if you have any array-based data structure, you can make it persistent. At which cost? Array operations are constant time, of course. Now, logarithm n time. Array memory is like 1 per element. Here we have 1 per element initially also, the constant multiplier of 2. But logarithm n for each element of after for the element which we are modifying. So the new revision of each element costs logarithm. So logarithm n slow down and logarithm n grows in memory, and we can make any data structure persistent, almost any data structure like persistent. Any questions so far? Please.
When you do deleted nodes that you create when querying, what's the upper bound for?
Even if you delete nodes that you create when reading queries, it is all. Please remember that it is also only needed when you have pushes. You don't have pushes. In case of arrays, you don't have pushes because you have only single element modification.
Yeah, but like what's the upper bound for the factor? Is it still 6?
If you delete nodes, then I think that reading operations do not create new nodes. Actually, they all delete them. And the writing operations depends on what you do with pushes. So writing operations, pushes must be saved because they cannot be rolled back. Because in this case, you modify along the path. So since you have other modifications, you cannot roll back the pushes. So in the most functional implementation, you will, if I am not making a mistake, you have like 6 nodes per query. Per node on the path to the query, which is 6 floater. Like here they are. 1, 2, 3, 4, 5, 6. Okay. Now we have actually 2 more things I would like to say. The third thing is 3 more things, 1 small and 2 big. What is our lunch time? Like 4. Okay, let's move on anyway. So the small thing first. Queue. How do you make a persistent queue? One, well, when you have stack-based, list-based stack, maybe you can make list-based queue. So we have head, we have tail. So we push to tail and pop from head. But this is where our node copian method gives us problems. Because let's see, if we direct our arrows like this, so we go head nose next, then nose next, so on, tail nose, it has no next. Then pop is easy again, so we can from head tail we go to head next. Yeah, it's okay. But push doesn't work. Let's see. If you create a new node after tail, then the old tail now should have this as next. But we cannot modify this because we do not modify anything. We have to create a new node for the former tail. Now the previous node to the former tail again have the new and so on. So in node copying method for creating the list implementation of queue, push operation was n new node. We could try to reverse those arrows, although it's not clear, of course, how to make pop in this case, but okay, let's. It will not matter anyway, because in this case push again would be easy, like in stack, but pop is impossible to do for 2 reasons. First, we don't know the new head if our arrow points backward. And second, the new head should have the previous element equal to null, so we should copy this and so on, and in this way pop would be linear cost. So there are actually multiple options to make queue. One of them is make array-based queue using our general technique of segment tree. And this is what I would recommend actually, because it's the simplest way. There are other ways. I will not use our time now to give other logarithmic ways, but I will give an example of what is better, a bad idea how to make a queue, and the why isn't that. You might have heard about queue on 2 stacks. Did you hear about that? So you take, it has very nice visualization. So you make the queue. How does queue work? You get here goes push, here goes pull. Let's build the wall in the middle of this tunnel. So when you push, you go inside and pile up in front of this wall. when you make pop, if there is somebody who is able to do pop, it is pop. If there is none, then all these guys go from there to there. They, since these steps have opposite directions, they will be reversed and they will be in the same order here, looking from the point of view of the cube. And then they can walk away. And if it's not persistent, if it's already a queue, then it's amortized constant time per operation, because for every element that is pushed and popped, it has 3 events in his life. He's pushed, he's moved from one step to another, and he's popped. What goes wrong? If we try to make this persistent, we already have persistent step, so why wouldn't it be possible to make a queue with 2 persistent steps? The answer is because persistence and amortization doesn't go together well. Why? The reason is that what is amortization? It is averaging actually. We are looking at, there are some expensive operation like when I have to move all the elements from the back step to the front step. And another like amortized data structure, there are also, for example, vector. When we tuple its size, it's an expensive operation, you copy all of its elements within the unit in size. But these expensive operations happen rarely. They are infrequent, so they are compensated by a lot of cheap operations. So in this case, to make these n elements move there, we have first to push all these n elements. So if we, like accumulate time when we push, we charge 2 and not 1 for this push. 1 is saved and can be then used for this operation. But if we have persistent, then this expensive operation can be forced to be made again and again and again. So we update our data structure, moving it to the state when the next operation will be expensive. And for that revision, we do this operation, it's expensive. Then for that revision, we do this operation, it's expensive again. And so on and so on. So amortization there are actually some data structures that are not purely functional, that are tricky, constructed to be still amortized. But this is a rare case. Usually, it's not like this. Usually, you could not use persistence together with amortization. So you can, for simplicity, use this rule. But if your data structure is amortized, it doesn't work to make it persistent. So Q on 2 steps doesn't get persistent. So only the queue-based, array-based queue and segment-based persistent array work. Okay, now we should use the word that I have recalled, the confident data structure. That will be 3. The result? What is the problem with the trip? Let's see. So for trips, we have, how do we usually program trips? We have like 3. Every node has, well, we will use a so-called implicit T trips. It's also called rope data structure when we have like an array that can be cut and concatenated. So no keys. Just we know just the order of elements from left up right traversion of the chain. So that is first, second, to do this, what do we do? We store the size of the subtree, yes, in the tree. So we store the size. when we want to get the fifth element, we see if the size of the left subtree is smaller than 5, then the subtracted size will go to the right, and if it's greater or equal, then we go to the left. And we also store additional key called y usually, and that's why it's sometimes called Cartesian tree. Y is the random key. So we create the random value, and it's heap-like structure for y. So the y's go, for example, like direction. So when we make, for example, merge, how do we do merge? We see, we take a look, If the y key of A is less y key of B, then we say that A right merge A right B, which are A. Else we say that B left is merge A left, and also we have some parts here, like in segment 3, where am I? If one of the trees is null, then we just return the other. So this is merge. How can we make it persistent? The first thing we should do is fix this. You know, we cannot modify the values of the fields. So what should we do? Here. Create new nodes. So instead of this, we say that mu A is mu node. Here left is the same, y is the same, right is merge A right B. And here is the same about UV. If we do this, we get a fully functional and fully persistent tree, but not confidently persistent in a sense that, yes, you can merge two revisions of the same tree, but the time complexity is ruined. Why? Because if you take two, we use the same random keys, so if you merge the tree with itself, merge two revisions of the same tree with the same root, then they will all have the same y value, and this randomization will be broken. So it's like if we merge it with itself, merge it with itself, we now have 8 nodes, but all of their y keys are the same, so there is no reason in that y key at all. How can we fix that? We replace tree with alternative data structure, which has the same properties and the same time running analysis, but it gets confidently persistent with this operation. Instead of using y keys, we just use randomization every time we merge. What is the reason for randomization in trees? Why do we make this random keys and compare them here? The main idea is, and the analysis, the time complexity analysis of this randomized data structure is based on the idea that we want every node to be the root with equal probability. You can see that it is actually the case. The minimum value is in any node with equal probability, of course, because of symmetry. Can we get the same result without storing these y keys? The answer is yes, and it is called randomized binary search tree. How do we do? When we want to merge two RBSTs, we have now the idea, the inductive hypothesis that in this RBST every node is the root with the same probability. Say here are A nodes, so 1 divided by A. Here every node is also a root with the same equal probability, which is in there are B nodes, 1 divided by B. What we will do now, we will choose this node to be the root of the new tree with the probability of A divided by A plus B, and this node to be the root of the new tree with the probability with the rest probability with the remaining probability of B divided by A plus B. And in this case, each of these nodes will be the root of the new tree with the probability of 1 divided by A. It is already there, times A divided by A plus B stays there, equal to 1 divided by A plus B, and same here. So instead of this, we write random FIA size plus B size less or equal, well, less actually is from 0, yes, A size. And get the same result. But now this randomization survives persistence because it doesn't use any stored keys. So every time we merge anything, we make this decision randomly. So if we do this, the sizes are the same. So with equal probability, we'll have one of the roots. Now, what I was talking about in the beginning of the lecture, we have like 1 node here, 2, 4, 8. But if we do it some more times, maybe we can get like, I don't know, 2 to the power of 100 nodes. How many new nodes actually are created? Well, it's proportional to the depth of the tree. The depth of the tree is approximately logarithm. Well, there is a constant factor. Let's say it's approximately 2, I don't know. So it's like 2 new nodes, 4 new nodes, 8, 16. No, not 8, depth. So 3 new nodes, 4 new nodes, 6, 8, and so on, 200 new nodes. So actually we have created only, well, approximately 14,000 new nodes, 20,000 actually. But we have 200 virtual nodes, yeah? Just we didn't access them. Because when we merge, we have this, if the segment tree, persistent segment tree reminds me of octopus, I don't know what would this remind me of, because it's actually wide. Wait, let's try to make this. So when we have a node, then we have merge it with itself, one of these becomes, so we create a new node. Then we merge it with itself, one of the nodes is created as a new node, for example this one is left, and its right is the merge of this and its former, well, no, its right is empty and its left is merge of this and its former left. So the new node will be created with this left and this. So, and the further we go along this path, there will be a new, and one of the same node will be accessed by multiple paths actually. If you would like to use this array to store the real data, the actual data, then you will have to split out some elements that you want to fill with some data and merge it back, and so you will again have this virtual zeroed out very long array, and single elements there would be merged out from other revisions that contain your actual data. So in this case, you see that the same if in segment tree everything was a real tree. Here in a tree with persistent implementation doesn't have a real tree. If we merge something with itself, the parts are used for different segments of the rope stored in this tree. So again, to make the tree persistent, we change almost nothing. Two modifications. First, you create new nodes instead of assigning. It's even a smaller change for this than it was for a segment tree. And second, you get rid of random keys. Instead, you use randomization every time in merge. In split doesn't use Y keys, so it's okay. Split only changes in the sense that instead of assigning, you create. Well, I have one more thing to tell you before we're going to lunch. Is to connect the two things, the scanline and the persistence. That's simple. Let's get back to our problem. We have points on the plane, and we have rectangular query. And we want to answer the number of points inside the query. Let's recall that we have so-called offline settings for this problem. What does it mean? The first step we did was to make a single list of events, the beginning of the rectangle, the end of the rectangle, and the point. And that's why it's called scanline. So we like to go on with the scanline along our plane, and when we get the event, we process it. The main requirement to be able to do this is that we know both points and rectangles beforehand, because we want to put them all into the same array and sort them. But what if we have points beforehand, but queries are so-called online? So we have new queries coming one after another. Can we deal with that? The answer is yes, we can. First of all, let's do the following. Let's do the same scanline, but without rectangles, only with points. What do points do? When we meet the point, we make +1 in our segment tree for this position. Let's use not a segment tree, not an ordinary segment tree, but a persistent segment tree. If we use persistent segment tree in this problem, then we have all revisions at all interesting positions, or significant positions, over a scanline. They correspond exactly to the revisions of the segment tree. Before anything, after the first point, after the second point, and so on, after the last. So what would we do when we get a query over rectangle? Well, easy. We find the revision of the segment tree that was at this position. You find the revision of the segment tree that was at this position. And we just subtract the sum here minus the sum here. And this is the number of points inside the row. And this is actually a general technique. So if you have some problem that can be solved in offline setting, this is usually applied to a data query problems. Here we have data points and queries on this data segment. So what do you, rectangles. So what do? You process the data as if there were no queries, but in using a persistent data structure instead of the usual data structure. You store the revisions you need. After that, when you process queries in the online setting, when you have a query, you check those persistent revisions that would be needed if the query was known at the moment of processing, and answer the query. So this is the canonical example, but there are similar scanline and scanpon examples that use the same technique when queries are online. Unfortunately, it doesn't easily generalize to the case when data is also known online or changes online. But you cannot get everything at once. At least you can make queries online with it. Okay, so I think that we have covered most of what I wanted. Now, I don't know where and how we will make lunch, but I think we will have after the lunch. You go to the site, I don't know, did you get the link to the site? It's called Brazil 2026.opencap.org. So you can, if you wish, if you have some time between the lunch and the contest, get into so-called trial contest to get used to the system. If you wish, you could do it yesterday also, but sorry. And at, I think, 1 p.m., we will start the contest. It is 5-hour contest. Immediately after the contest is over, you will get a tutorial for the contest that will be right inside the testing system. You can read it if you like, or if you would like to solve before reading the contest, it's up to you. We will not have oral tutorials, discussions, but if you have questions, you can address me, I think, in the break tomorrow or before or after lunch tomorrow. That's it. So thank you and have a good lunch.